Okay, yeah, once again, good morning. So we will start with a quick recap. Hold on, I think I need to share the screen. Okay, guys, please let me know if you can see this screen. Can you guys see my screen?
Yes, sir.
Okay, great, nice. So we'll get started with a short recap. So previous class we saw about ROM and RAM, right? Like the types of memory and different functionality of that. Let's have like a small like Q&A session on this recap to know that how much you've understood this. So let's take ROM. So somebody wants to explain what is a ROM. Nitin, are you here? Let me pick some of you by name. Okay, the first name here, Mehul. Mehul, can you hear me? Okay, Ishita started with her attendance. Okay, let's start with Ishita then. Ishita, can you hear me? Okay, guys, come on. So, did you guys understand uh, what was discussed in the last class? We had 99% attendance last class in all three sections included, right? There was only one absentee. So, I'm sure like everybody would have attended the session. But the only thing is, the question is whether you've paid the attention. Okay, so make the best use of this time. Okay, so we are also investing a lot of time in this, so please do understand that. Okay, and it shouldn't be uh, like just a time killer for you guys too, right? So it should be useful for you too, so please listen in the classes. Okay, we'll get going. So to give you a quick recap, so ROM is actually a read only memory. Okay, so there are two types of memory. So one is read only memory, and then the other one is random access memory. Okay, so these are the faster access memory. We are not talking about storage devices yet. So although we will see them down the line. So first we will start with ROM. ROM, as I mentioned, is a read only memory where it's only meant for reading specific bits of data. Okay, uh, compared to ROM and RAM, ROMs are slower. Okay, and RAMs are faster. So which makes it which makes ROM like as a not like a very performance oriented memory. But still, why are we using ROM? Is because they are cheaper. Okay, they are much cheaper than the RAMs. So the in the ROMs, so if you see, this can also be uh, seen as the technological advancements of the ROMs. So to start with, there is something called as MROM. MROM is masked ROMs. So these are like one time programmable ROMs. Like these are like when they are fabricating, so the memory is etched. It's done at the fabrication level. So once you're doing the fab, it's done. So you're masking it, and then it's like it's a hardware. It's designed to read those bits. Okay, so you cannot alter them by any means at all. Okay, so those are the masked ROMs. The second one you have is programmable ROMs or one-time programmable ROMs. These are little bit different from MROMs in the sense that, so for every bit of data or every bit associated with this ROM, there is some kind of a fuse. Okay, so so every chunk of memory, you actually have a set of fuses to to actually write or not write. Okay, so meaning uh, so you will actually get the memory from the fab, and then you can for every memory location associated, you can either blow the particular fuse or not blow the fuse. So there's something called as a fuse, and so if you blow the fuse, it will read a bit value, and if you don't blow the fuse, it will read another bit value. So in that sense, it is one time programmable, but in all other terms, it's also like your MROM. So once the fuse is blown, so it's done deal. So you cannot change it ever again. Okay, so that's about the PROMs or on time programmable ROM. So there's another thing called as EPROM, erasable PROMs. So where you can erase the data and you can program it, but the thing is this is not very flexible. So so the BIOS chips that we see, right? So they are all like EPROMs. So what will happen is, so there will be some BIOS setting that you may want to change. Okay, so now we do it like these days. The computers support like different technology, but earlier what they used to do, even now in testing, what they do is they have EPROMs for BIOS. So every time you want to change a BIOS configuration or you want to reprogram the BIOS, you take the chip out. Okay, you take the ROM out, and then you put it on a specific device, and then you burn it. Okay, meaning like you program it. It takes a while, so it takes like around like half an hour for you to do the entire process end to end, from you disassembling the platform, and then take the BIOS out, put it onto the new the device, and then write it. And then after the writing itself takes some time, and then again you have to reinstall it back. So it takes roughly like 20 to 30 minutes of your time. So this is again not very flexible, but it does allow, it's still better than your MROM and PROMs. You guys can hear me? Hello?
Yes, sir.
Yeah.
Yes, sir.
Okay. And next we have the EEPROMs. These are electrically erasable programmable ROMs. Okay. So they are much advanced. So they use a technology where it allows you to electrically say electrically program it, meaning like you can change the values of you can actually switch on or off like a particular bit, meaning you can program it. You can add the weightage to every single bit, so that when they get charged, they read bit 0 or bit 1. Okay, so these are getting quite popular these days. So most of the ROMs that we see nowadays are EEPROMs. One good example of EEPROMs is flash ROM. We all use these pen drives, right? Flash memory. So that's actually a EEPROM. The way flash memory works is it's actually very interesting. So it uses as I mentioned, it uses the EEPROM as its technology. But then what it does is, so inside the flash ROM, so it is divided into chunks of blocks. Okay, so like this. And now, so this particular, the small square here is actually block of memory. Okay, it's not just one bit, but it's just blocks, and it's a block, a decent block of memory. Okay, so now let us say you want to write something to this. You want to just modify a particular file, right? You've just changed some bits here. So what it does is, instead of like programming the entire thing off, right? So what it will do is, it will actually copy this content to your system. Okay, there's a buffer storage, maybe you can use a RAM or something. Okay, and then it stores the contents here, whatever content it is, and then it modifies whatever you want to do inside your buffer, and then what it does is, it writes the entire block back. Okay, all this is done in like a flash. Okay, so that's why they termed it a flash ROM. So what it does is, it takes the entire block. So even if there is one bit that is changed inside this block, you will have to take the entire block out, and then you rewrite that bit, and then you have to put back the entire block. So you can only erase a block. It's block erasable. Okay, so that is how the flash ROMs work. So by this, the good thing is that you've actually separated the other blocks. Okay, so if you want to write one, previously what would happen is, if you want to write one bit of memory, so the entire ROM should be like programmed. So that will take a long time. So the invention of flash, actually, by dividing it into blocks, actually enabled much better read and write. So even though it is called ROM, read-only memory, it is not read-only memory, right? Flash is a read writable, but then the name just stuck to it. So next we come to RAMs. Okay, so RAMs, we have SRAM, DRAM. So these are the two main categories. So SRAM, as we saw in the earlier class, is made up of 6 to 8 transistors. Okay, and it's very fast, because it's everything is transistor, right? So it's very fast, and also it's one of the fastest memories available, next to, of course, the flip flops. But the downside of it is, it's very expensive to fabricate SRAMs, and the other thing is, it's very power consuming. So the next thing is DRAM. So to overcome the limitations of SRAM, we have DRAM. So by the way, for SRAMs, cache are your examples of SRAMs. Okay, so beyond the cache, we are not using SRAMs anywhere else. Now coming to DRAMs, DRAMs is dynamic RAM. So it's called dynamic because it has to be dynamically refreshed. Okay. So the other thing is, in DRAM there is only like one transistor and then one capacitor. Okay. So based on that charge of the capacitor, you will come to know whether the DRAM has a bit 0 or 1. The downside of it again is that the capacitor's charge decays over time, and so if you take a capacitor, so the characteristic is going to be like this. So, and this is time. Okay, and this is going to be your charge. Your charge is q, right? Sorry. So your charge is going to come down. Okay, so exponentially it's going to decay. So what you have to do is, you have to pump the charge beyond a certain time. So let us say you'll call this as a 1, and you call this as a 0, right? So then your 1 will slowly become 0. So you will know the time, right? So before this time, you will have to keep refreshing it, so that it actually maintains the state 1 if 1 is programmed. So that's your DRAM. Again, the downside is, you have to keep refreshing it. So now there's something called as NVRAM. So what NVRAM? NVRAM is really interesting. It's non-volatile RAM. It's basically SRAM, but SRAM. Oh, sorry. It's basically a DRAM, but that is connected to a battery. Okay, so you have DRAM that is connected to battery, so you will have a continuous charge in that. So battery, you can say, you can actually charge it once in a while, but you have a continuous charge going on in the NVRAM. Okay, so that's about the recap. Any questions so far? Hello guys,
No,
any questions? You guys understood something? Did we get a good recap?
so could you repeat NVRAM?
Yeah, okay. So in NVRAM, so the RAMs need continuous charge, right? So what you do is, you connect the RAM to a battery. Okay, whenever you want to pump charge, So you connect it to a battery so that the battery will keep supplying the power to it, so that the state is maintained. Okay. uh, because the difference mainly between RAM and a ROM is that RAMs are volatile. Okay, so this is volatile, which means that it will lose the charge. Okay, so for example, whatever you have stored in your RAM, if you power off your system, right, the RAM's content will be lost. It will become everything will become zero charge. Okay, so which means it's volatile. Your bits will be lost. So in order to maintain the state, right, so unlike ROM, it's read only, right, so you store the bit and it will stay forever. Okay, so, something similar to if you take your flash pen drive, right, so you write something to it and then you remove it from the device. You're not charging it. Okay, since you're even if you're not charging it, next time when you plug in your device, you will still see the data. That's the advantage of ROM. However, in RAM, that is not the case. The moment you remove the charge, the bits are lost. So to overcome that, what you do is you connect this RAM to a battery. Okay, so even so there will be like a device connected to a battery, so even if you remove it, you will actually maintain the bits for some time until the battery charge is there. Okay, clear? Is it
Yes,
clear?
sir.
Yeah, okay,
Yes, sir.
great. Okay, so we'll see the concept of memory shadowing. Okay, so memory shadowing, so this is it's actually like kind of like a buffering technique. So what happens is, so you take I mentioned about the BIOS, right, briefly. So there's something called as BIOS, basic input output system. Okay, so what is BIOS is that it has all the initialization and then the configurations of your system for it to boot. Okay, so if you have seen, if you own a laptop or a computer, right, so you would have seen BIOS coming up. If you go inside the BIOS, you have so many configurations. You'll have a memory configuration, and then you can enable or disable your PCI, or your power settings, or your performance settings. Okay, and so there are many things. So you can even uh, actually you can even change certain addresses. Like if you want to configure your particular IO device or a memory device, you can choose which secondary storage you want to boot your processor from. Okay, so basically it's a configuration for your computer. It is stored in a ROM. Okay, so now what happens is, so ROM is a read-only memory, right? So and then it generally is a programmable ROM, but it's not. It cannot. It's as I said, it's slower. ROMs are slower than RAMs, correct? So RAMs are faster, but ROMs can store the value forever. Okay, so it is non-volatile. Okay, so you store this configuration. You want to store it forever, so you put it in a BIOS. You program it, and then you store it in a BIOS. Now, when your computer boots, if it has to read every configuration from this BIOS, it is going to take a lot of time, correct? Because ROMs are slower. So what you do is, you just, once the system boots, you just copy the contents of this ROM into a RAM. Okay, so now you copy it to a RAM. Now the system is powering up, your RAM is also up, right? So the same configuration, you will at a time you will copy it in a bulk. You copy it here, the configuration. So it's not going to be like one time I read this, next time I read this, next time that's going to take a lot of time. So what you do is, you do a bulk copy to RAM. Okay, and this is your CPU. So this is your CPU. So your CPU is going to read all the configuration from the RAM and not from the ROM. But it is thinking it is reading. So the address will be the ROM address, the boot address, right? So there is something called as a boot address, as you have seen in operating systems class. So there is something called as a boot address. It's also that's why it's also called as boot ROM, if you remember, right? So it's called boot ROM. So that boot address will still be copied here. Your virtually you will be addressing the ROM, okay, but the contents will be copied to RAM. So that's why it's called as a shadow. So this RAM is actually a shadow for your ROM. Okay, clear? So it is mainly done to save the time. Okay, any questions, guys? Any questions? Is it clear? Okay. Okay. So next we have types of memory interface. So there are actually three types of memory interface. Like one is a parallel interface, the other one is serial interface, and there's one more not so popular, but it's called as a single wire interconnection. If you take parallel interface, um, so I don't know, even now some of the desktops will have these parallel interfaces. If you have seen, there will be like a very wide bus, or like a wide set of wires, right? If you've seen, that connects to your hard disk. I don't know how many of you have, I mean, how many of you remember this? Before we have the SATA cable connected to the hard drive, right? So we used to have this parallel interface. Even now, if you have CD-ROMs or external CD-ROMs, you may have to connect it to through a parallel interface. So uh, it's going to look like this, right? So you have multiple wires here connected together, okay, and then you have the connecting port here. Okay, so that's your parallel interface. So every single line here corresponds to one bit of your signal. Okay, so it's going to be multi bit wide signal you want to transfer. You'll transfer the bits parallelly, so you'll transfer it in 8 bits or 16 bits, like that. You transfer it that way. Okay, but it has several limitations, especially with respect to reliability and fault tolerance perspective, right? So you have a lot of issues here. So that's why you go with the serial interface. Serial interface became a popular thing, and also this is not very scalable. So now we are talking about 64-bit architecture. So now in this case, what will happen is you cannot have like a 64-bit wide port, right? So it becomes like very space consuming too. So to overcome that, we have this serial interface. Okay, so the serial interface, an example is the SATA cable that we see, right? And there are also other serial interfaces like UART. You must have seen our projectors, right? How we connect our projectors. So those are actually serial interfaces. So if you remember the port that we connect the projector to, right? So that one, all those are serial interfaces. And finally, you have your single wire interconnection. So it just has one wire, and so this is for very small systems where you don't want complex protocols. So where there you just have like a single wire interconnection. Okay, all right. So any questions on this? Just go to the next one. Okay, so that's about the memory and the memory interface types. So next we have sensors and actuators. So now we will move on to the other parts of the embedded system. Okay, so now whatever we have seen, the first thing we saw was the CPU, the core of an embedded system, right? That is nothing but the CPU. Okay, so it can be like the CPU, or it can also be microcontrollers, and there are different types in that too. Okay, so like we saw like ASICs, COTS, and then PLDs and things like that. So that's the core of the embedded system. The next topic we saw was memory. Okay, so we saw different types of memory, and also the interface part of it. Now we move on to how the embedded system communicates with the outside world. Okay, so that's what we will see. So it starts with sensors and actuators. Okay, sensors are basically your input devices. Okay, your input devices, and your actuators are output devices. Okay, So the definition goes like this: it's a transducer device which converts energy from one form to the another for any measurement or control purpose. Okay, so whatever takes so it has to talk to the outside world, right? So all the just simple transistors can only pass electrical signals. Okay, so but here we need to convert from some other form of energy to electrical signals. Okay, so one typical example we can give is temperature sensor. Okay, it has to sense the heat. Okay, you need to have a special device that converts the heat energy into the electrical energy or voltage. Okay, so it's like that. So you, in some sense, you can even call your cameras as sensors. Okay, so wherever you actually convert heat or light or any other pressure or anything else, right? So any physical quantity, any physical dimension, if you want to quantify it, measure it, you use a sensor. And as I said, it's an input device. An actuator, on the other hand, is the output device. So that's also like a transducer device. It is mechanical or electrical device. So it converts the signals, electrical signals, into physical action. Okay, physical action or motion, or it's like a physically you do something to it. Okay, uh, typical examples would include your motors. Okay, so where you have this rotation, rotary motion, right? So that's what you do. So the embedded system goes like this. So you take the sensors, you actually get the data from the environment through the sensors. Okay, and then the controller controls it, and then your actuators will respond to it, and then the feedback goes. Okay, for example, this could be like your temperature. Okay, you take the current temperature, and then you compare it with something that you want to set it to. So you compare the outside temperature to whatever you're setting it to. Then if the temperature is more, then you actually you trigger the control for the AC. Okay, so then your actuator will actually, it will trigger a relay or something that will relay, or it will control the motor of a fan or something to control the airflow. Okay, so based on that, now the temperature will slowly come down. Okay, and now it becomes 24 degree C, which is lesser than the set one. So then you'll have to control it again. Okay, so back and forth you move. Okay, so that's how the feedback goes. Okay, any questions? Are you able to follow? Hello, guys.
Yes, sir.
Can you guys follow?
Yes, sir.
Okay, nice. Please respond. Okay. Otherwise, I don't know if my mic is working or not. All right. So we'll just see. So I think here the same example is given. Okay, so your temperature sensor takes the input, it sends the signal to the control center, and the control center adds some intelligence to it, and it's going to trigger up or down the it's going to trigger the actuator. Okay, so here we have an example where it turns on a sprinkler. Okay, so if you have like a fire, temperature is, there's going to be like a temperature detector as well as smoke detector. So based on that, you're going to trigger a sprinkler. Okay, so that's how the entire control goes. So some of the examples of the sensor and actuators are follows, like temperature sensor, proximity sensor, accelerometer. There's a big list. There's a color sensor, humidity sensor, and lots of things. Okay, so alcohol sensor, I think you guys must be aware of this, like where you have the alcohol, like you check the content of alcohol in with someone, right? So you blow onto something, some device, and you the meter shows you how much I mean how much drunk the person is. So there are lots of sensors involved. Similarly, in the actuator part, you have electric motor, stepper motor, relay. And these are the most widely used, especially for something that we will be working on. And there are many more. There's lots and lots of actuators involved, and these are all related to the mechanical side of it, especially in the factories where you have the automation, right? In industrial automation, so they use lots of actuators here. Okay. Next, we move on to typical embedded system, the I/O devices. So now earlier we saw the sensors and actuators. Again, sensors were inputs, actuators are output devices. Now, in addition to that, there are standard or what to say mainstream I/O devices. Okay, so these are what we generally use in our general purpose computing too. So these I/O devices include these like keyboards, your optical pen, barcode reader, and things like that. And your output devices are your monitor, headset, headphones, and all these things. Okay, and there are some I/O devices too in between. So it can be considered as both input and output device, like your pen drive and things like that.
So,
Yeah,
the headset there, it's in the output part, but shouldn't it be like input also because there's a mic attached to it?
yeah, that's a good point. Yeah. It actually does. Yeah, correct. Good point. So the mic here acts as the input device, so it has to be in between. Correct. You're right. Okay. So we'll see some of the I/O devices. So we'll start with your LED. I'm sure like you would have uh, you know the basics of the LED, right? Like LED is light emitting diode. It's basically a diode. It exactly functions like a diode, except that it also gives out emits light. Okay, so that's about the LED. So so basically it's a PN junction diode, and so anode is connected to the positive side, or the higher voltage, and then the cathode is connected to the lower voltage side. Okay, and when you forward bias the circuit, you get the light. Okay, so so basically there are different voltages that you can supply to get different colors, but the only thing is you need to make sure the LED that you are using can actually withstand that. Okay, so how much voltage you are supplying, it has to be within the specified range for the LED to work. So generally, a resistor is used in series. So you use a resistor in series to the circuit for the circuit to work. Okay, it's similar to your forward bias circuit that we have seen. Any questions in this? Is it clear? So basically, it's a forward biased circuit, a forward biased diode circuit, where the diode when there is a forward bias, it also emits a light. That's all. So in LED, right? So you use LEDs in many places these days. Now we also have LED TVs, right? So everything works on the same LED principle only. Okay, but the very popular ones or widely used ones include the 7-segment display. You would have seen this kind of display from banks to everywhere, right? Any counters or anywhere we go, we see this. It's a very it's a cheap and also very effective display that can be used. So basically, it has 7 segments, as the name suggests, and also there is a decimal point. We've seen this in calculators too, if you remember. So in calculators also we have the same format. So you name these LEDs. So basically these are 7 different LEDs, and there's an eighth one too. It's named from A all the way to G, A B C D E F G, and then there is a decimal point. Every single one is connected as a different LED, and you control it. You actually have like a lookup table where you will say which of the LEDs should be switched on. For example, if I want to display 2, it has to be like this, right? So it will be like from A, B, C, D, E, F, G, and then there is a decimal point. Okay, so if you want to display 2 here, what you will do is so your A should be 1, your B should be 1, your G should be 1, okay, and then your E should be 1, and then your D should be 1. So the remaining ones are zeros. Okay, so here these two are zeros. Okay, and this will be your output. So you send this to the output port, and that actually goes through these pins, and then it's going to highlight only those particular LEDs. So it appears as if you got the number 2 displayed. Okay, so that's how it is. And there are two ways to connect these pins. Okay, so far is it clear? So how the 7 segment works?
Yes, sir.
Thank you. So there are two ways how you can connect this. So as I said, these are nothing. LEDs are nothing but diodes, right? So what you can do is, so the diode looks like your LED is going to look like this, right? So each LED is going to look like this. So this is your anode, and this is your cathode. So anode and then your cathode, right? So you can actually connect, have a common anode. Okay, just connect all the anodes to a higher voltage. Okay, and then you have different cathode pins. Okay, so now you supply the voltage, you connect these pins to you program these pins differently. Okay, so that the circuit gets completed or not. You decide whether the circuit is going to get complete or not. The other way to do that is, you have a common cathode. You connect all the cathodes together, and then you actually complete the circuit only for selected uh, uh, LEDs. Okay, so there are two things. So one is common anode type, and the other is common cathode type. So as I said, we are going to have the port in that order, right? So we are going to send a stream of parallel bits, right? So the A segment goes to the least significant port pin. So when you want to supply, I mean, you want to send this to the output port, your A is going to take the least significant bit position, and your DP is going to have the most significant bit position. So it's going to be A, B, C, D, E, F, G, and then finally you have your DP. So you will send the bits accordingly. So you'll say 1 1 0 1 like that. So it corresponds to A, right? So you'll actually feed this to the output port. Okay, and as I said, the current through each segment can be limited by connecting a current limiting resistor. Okay, so you connect a resistor to this anode or cathode of each segment. Okay, so to make the circuit complete, right? To have the forward bias circuit. Okay, any questions on this? Is it clear?
Yes, sir.
Okay. So next we have this optocoupler. So optocouplers are a special type of circuits that actually helps us to isolate two different circuits. Okay, so for example, let us say you have a very low power device. Okay, so let's take this particular figure here on bottom right. So what happens is, so this is it's a low power device, and you want to isolate it from any high power input or output. Okay, you want to isolate this. So what you do is, you have an optocoupler here and an optocoupler here. Okay, so the optocoupler works like this. So you have your IO interface here. Okay, and then you have a photo transistor. Okay, and then you have another transducer here. Okay, so the from the light emitted by the LED, so this transducer is going to get triggered and it is going to change the voltage, or it's going to alter the voltage for the other device. Okay, now the good thing about this is that, let us say you have a sudden spike of your voltage here. Okay, in the absence of an optocoupler, it can actually harm, it can harm this particular circuit or low power circuit. Okay, so this, let's say this is our low power microcontroller, let's say. So it can harm us. So what you will do is you will use an optocoupler here, and then whatever high voltage that comes in, that's just going to be emitted as a light. Okay, and even if it's going to damage, it is just going to damage this particular circuit. Okay, this particular interface, and it's going to leave the rest of this untouched. So it's this is not going to get affected. Okay, so it's only going to work on the light, and based on the light it's going to change the voltage. Okay, so that is how the optocouplers work. So it is typically used to reduce noise or to isolate your low power device from high power input output devices. Okay, any questions? Okay. Next, we have relays. Relays are one of the most widely used actuators. Okay, so the relays are nothing but it's made of like a kind of a solenoid. It's a coil. It works based on the principle of induction. Okay, so what you have is you have a magnetic switch here, and then you have a relay coil. Now, when you supply voltage, this is going to create an inductive. Yeah, it's going to create an electromagnetic wave, that's going to electromagnetic field, that's going to affect this switch, magnetic switch. Okay, so based on it's, you can imagine something like there is a magnetic sensitive switch here, and then you have a magnet here. So when you want to switch, you want to close the switch, you will supply the voltage, and it's going to create a magnetic field. It will attract the switch, and it's going to get connected. Okay, so it's kind of a switch, a magnetically controlled switch. Okay, all right. So relay will typically have a driver too. So if you see in this, a transistor is used as a driver. So basically the idea here is that transistors are nothing but they are electronic switches. Okay, so they are also switches. By supplying voltage here, you're to the gate, you are going to have the voltage flowing through your source to drain. Okay, so based on the voltage you supply to the gate, you can switch on or off a particular circuit. Okay, so when you want to switch on a relay, you will use a transistor to switch it on. Okay, so you use this transistor switch to control the relay here. Okay, so that's the idea. Any questions? Any questions, guys? Is it clear? Next, we have push buttons. Okay, I think you would have seen this. This is a very familiar thing that we see in our microcontrollers lab, right? So you see different kind of switches, push buttons and switches and all these things. So all these are types of push buttons. Okay, so the idea is something like this. So there are two types of push buttons. So one is push to make and push to break. Okay, so the symbol is something like this. So this is push to make. So when you push the button, it's going to complete the circuit, and it's going to send the what to say, it's going to complete the circuit, and you're going to send the electrical signal. And push to break, on the other hand, is something like this. So you push it, so the by default the circuit will be complete, you'll be at a higher voltage, but when you want to break the circuit, you push it. Okay, in many situations this is very useful. Okay, so the circuit diagram is something like this, right? So when you have uh, a push to make kind of circuit, what happens is, so initially your circuit will be grounded. Okay, but the moment you push the circuit, you complete it, right? So then the path of least resistance is taken, and then the circuit completes. On the other hand, push to break is something like this, where by default it is at high voltage. Okay, the circuit is already complete, but then once you push to break, then what happens is, this circuit gets connected and it takes the path of least resistance and it gets grounded. Okay, so that's the idea. Clear? Any questions in this? Okay, good. All right, so we come to the last part of today's lecture. Where we're going to see communication interface. Communication is one of the most essential parts of any computing device. If there is no way to communicate, there is no way to know what is happening inside the embedded system, right? So the communication should be from the input side as well as from the output side. There are two types of communication. So one is at the device level. Okay, so the device or board level, and the other one is product level. Okay, so the device level is to communicate inside the system itself. Okay, and the product level is to communicate to the outside world. Typically, we have your I squared C, SPI, UART, and other different memory ports we saw, right? Memory interfaces, something like that. Okay, so you use these in not only for memory interfaces, you also use it for communication between different processing units or processing elements. Okay, so let's say you have a DMI controller or a memory controller that has to be connected to CPU, right? It has to communicate to the CPU. So you use inside the system you have different components. Okay, so inside that, how do you communicate? So that's what these device level communication works. And the other one is the product level communication, right? So that can be of two types again. So it can either be wired or wireless. Okay, and it can be, again, it can be serial or parallel. Okay, so serial or parallel we already saw what are the different types. And in wired and wireless, in wireless you have this infrared, Bluetooth, Wi-Fi, and then RF, all the GPRS and all these things, right? These are types of wireless communication, Zigbee and all these things. And then you also have wired communication, where you have RS-232. It's nothing but your serial interface. Then you have your USB, Ethernet, TCP/IP, and several others, right? So we have different wired communications too. Okay, so with this we come to the end of this particular lecture. So you guys have any questions?
No, sir.
Okay, was it clear? Was it easy to understand?
Yes, sir.
Okay, good, fine. So
So
anyway,
is
I will be,
embedded system going to be mostly theory?
I'm sorry, what's that?
Is it going to be mostly theory for embedded system?
Yes, sir. This is going to be mostly theory. So there's not going to be much problems involved in this. Although there could be like one or two problem oriented when we enter into the operating systems module. But these are only the theory aspects of it. Basically, what they've done is they've taken the introduction portions of two textbooks and then prescribed that as a syllabus. Okay, so in some way it is easy for students to grasp. It's only the introduction part. We will not go deep into it, because many the feedback from many students, computer science students, was that microcontrollers and embedded systems course is way too electronics for us. So to overcome that, they have made it this way. Okay. All right, guys. So I'll stop recording now. Thank you, guys.